last week I was on stream. So I was like swimming from afar and everything. Like that night they might do this. I was like, it's cold. I'm Christian, like Southern California.
I would send you that. We'll go down to Texas one day. That's I'd rather be home. Sometimes I was like, hey, I wanted to go to Texas. Maybe it might be like that would really.
Yeah, what's up with the snow in like Florida and Texas? Kansas is like
it's like last time it snowed.
Get somebody like no trees.
It's windy.
It seems.
My husband.
All right. Drama.
So last time we talked about Hamilton. Well, last week I should say, talked about Hamilton paths, circuits, and then we spent a little time talking about some features of the complete graph with n vertices. In particular, how we could count some things about it, like how many Hamilton paths we had, how many Hamilton circuits we had, and how many edges. And remember the notation for the complete graph, in this case of n, and the number of vertices. So what we're going to do today is hopefully finish up chapter 6. And we're going to go through a few different algorithms on how you can find a Hamilton circuit or path or something close to it on the complete graph. It's pretty much exclusively on the complete graph because some graphs don't have Hamilton circuits. So these algorithms will only kind of give you something on the complete graph. There's a way of modifying that so that you get something on other graphs, but it may not be what you want. That's what we're going to do today. I should mention, so I did grade the homework from last week over the weekend. So one thing I noticed was a few people, not everybody, I mean, a lot of people did really well, but a few people seemed to struggle a little bit with some of the fundamental concepts. In particular, I saw a lot of, well, not a lot. I saw a few people struggling with degree of a vertex, and I just wanted to make sure that I made that clear. So if I have a graph like this, let's say, and I want to ask about the degree of one of the vertices, so let's say this red one, what is the degree of that red vertex? 3, right? And the reason is I can take this and I can magnify, I can't quite magnify as much as I want. Draw a little, oh, shoot, sorry. I can look at just that region, and what I'm seeing there is the half edges. I look at the things that are connected to that vertex, the edges that are connected, and I count them. Now, if I do that same thing, say, here with this vertex, what's the degree of that vertex? Also 3, right? Even though there's one loop, one edge, it's still degree 3 because there's 3 half edges coming out of it. That make sense? If you look at your homework and had an issue with that particular concept, feel free to ask me, send me a text or email, I guess. Also, some of the homeworks, I don't know what you guys did. Some of you uploaded it. About 5 of you uploaded it in a way that I couldn't annotate. I don't understand how that works. There are probably different options or something. So if you look at your homework and you don't see any comments, try uploading it in a different way next time. Because for some reason, I usually can write down what I'm taking off, but it wouldn't allow me to do it for like 5 homeworks. I'm not sure what happened. Maybe someone knows. If you'd like an explanation of your grade, you can ask me. Okay. So today we're going to talk about some algorithms. Find Hamilton circuits or paths. That's the least weight. Let me explain that. So one thing we want to do is we want to kind of upgrade our discussion of graphs a little bit so that it's really applicable to the world around us and the kinds of problems we might have. Okay, so here's an example. And we'll look at this example first. I actually went down the mileage between the different cities. So I looked at Lincoln, Manhattan, Wichita, and Topeka. Make a complete graph. And if we're interested in like making a circuit, like let's say we're a traveling salesperson or whatever, we want to go to visit each city, then, well, all of the circuits have sort of the same length, right? All the circuits will have what length? If I draw a circuit on this graph, how long is it in terms of the length of the circuit? What is the length of a path? The number of edges, yeah? So if I have a circuit here, and it's a Hamilton circuit, pardon me, a Hamilton circuit. What's the length of the Hamilton circuit? 3. 4. 4 is right, right? Like I have to go 1, 2, 3, 4 to make a circuit. However, that's not, if you're trying to do this, that's not, I mean, if all of them are length 4, that's kind of a silly problem, just choose any one. In truth, there's mileage, right? There's a certain amount of miles between these that you'll have to travel. So, at least according to Google Maps, these are the mileage, most efficient ways that we can drive between these cities. So we don't really want just any Hamilton circuit. We'd like to minimize the mileage, right? We would like to take the circuit that gives us the least miles. So we can Same one. Yeah. Oh, sorry, 130. Thank you. Okay, so this is what we want. Now, sorry, this is for later. So now the first algorithm, so this is what we call a weighted graph. This is called a weighted graph. And to any given edge, we call its weight, whatever that mileage is, whatever that number we're associating with it is. So we're interested in the circuit so that when we count up the weights of all the edges on the circuit, we get the lowest number. That's our goal. So the first algorithm we look at here is the brute force algorithm. This is section 6.3. What does it do? Well, what it says is, hey, we're on a complete graph, and we can write down all of the Hamilton paths. In fact, we know how many there are, right? Or let's say Hamilton cycles, Hamilton circuits, cycles. We know how many there are. How many are there? Huh? 24 paths is correct. So if I have, so that was my first question, you're right. If I amend that to my second question, circuits, how many Hamilton circuits are there? 4. The 24 you got because it was 4 factorial, yeah? Which is correct for paths. When we did cycles, we saw that for every path, we closed it up, we got a cycle, but 4 of those gave us the same cycle. We had 24 and we divided them into groups of 4. So we get 24 divided by 4 is 6. We can write them down. So let me write them down. I'll write Hamilton circuits. I write them down in a very funky looking way. Right. Here's my list. So L, M, so I go from Lincoln to Manhattan to Topeka, Wichita, back to Lincoln. So that's this path. That's that. Our circuit, sorry. Right, I'll go Lincoln, Manhattan, Wichita, or Lincoln, Topeka. Now, in this group of 6 possible circuits, there was some funky phenomena. And the funky phenomena was that I said a circuit really depends on like which way I'm driving, right? I can go in a circuit by driving one direction, or I can go that circuit going the opposite direction. Those are 2 different circuits, right, by our definition. However, if we're counting mileage, that'll give us the same mileage, right? We have the same road we're driving. It's going the opposite direction. So we can reverse the direction of these circuits and get the other 3. Not without affecting our weight count. And this gives us all 6. So what is great? So we know how to do this. Basically, if you don't know how to do this, what you can do is you can sort of look here and write down all the permutations of these 4 letters, starting with L. Okay, starting with L. Now, if you did that, you would get you would get all of these. But then you can sort of group them into reversing direction, as I did. Now, the brute force algorithm is exactly what you would expect. You just use brute force and you count. So we just add up, we look at the mileage here for this particular circuit, and we add up the mileage for each row, for each strip. So if I do that, and I did it beforehand, this. Of course, you can make a computer do this too. And last one is this sum. So we add up these mileages, and remember, because we're reversing direction, this mileage we get for both of these circuits. So here we found the mileage of all possible circuits that we have, and we look for the minimum. Pretty easy to identify. Just get this one here. So that tells us that these two circuits are the most efficient ways that we can travel to these cities. Make sense? So, great. So what's the problem here? So doesn't this just always give us the answer? Well, let me ask you guys, does this always give us an answer? Let's say we have a complete graph. We count let's think of it as cities if you want. You can think of it as planets or whatever. I mean, you can do whatever you want. But let's say we have cities, we have mileage between them, we make a complete graph. Can we always do this and find the circuit with the least mileage? Hamilton circuit with the least mileage? Can we always do it? Who says yes? Only one person? Okay, two people say yes. How many people say no, we can't? Sometimes we have problems too. Can vote twice. What? Questions? There's like a half raise. No? All right, guys. The answer is, I guess 1.5 people that said yes, we can't always do this are correct. We can always do this. But there's a problem with can, right? Can is a problem. You know what I'm saying? How many people know what I'm saying? So can is an issue, right? I mean, I can be an astronaut, right? But that's gonna be kind of tough. I have to lose some weight, I'm gonna have to grow a little bit, all of that. I can do things. Can is hard. See, we could do it, certainly we can always do it for this. But let's say we have like 11 vertices, 11 cities that we want to visit. Well, then the number of paths, number of circuits that we have is 20,160. Right? That's how many circuits we have. If I sign that for a homework, the 1.5 people that said yes, we can always do this, they can. And it's possible, but there's going to be a very long homework assignment. Probably there's going to be an error somewhere in there. I mean, of course, they could program a computer to do it. Okay, so then they say, okay, I can do it because I can program a computer to do it. But the problem with n factorial is, as I said last time, n factorial goes faster than exponential growth. And computers have a hard time with it, even computers, even the most advanced computers. Start getting into 100 vertices, they just won't be able to do it. It'll take them months or years or whatever. So, I mean, this is why, like for Bitcoin, they have these big data centers that they just choke through these math algorithms, and it takes forever, right? They, like the Bitcoin, you guys know about all this stuff? You guys don't know about this? Nobody knows about this? This is your generation. I'm old. I'm not supposed to know about this. You're all supposed to know.
Bitcoin is. I don't know.
How do you get
processes.
Bitcoin? How do you get Bitcoin?
Like,
Where does it come from?
currency,
From the ether?
electrical.
That's it does kind of come from electric. So there's math algorithms, right? It's called mining. You ever heard of Bitcoin mines? Oh God, what's wrong with you guys? You guys are in the young generation. You guys should know this stuff. Like this is the big controversy. They have like hearings in Congress about this.
It's like it's like online investments in a sense.
No,
Not the stock market.
there's like a real thing. You don't have real money, right? Join the club. So
One day, hopefully
no. So Bitcoin is like based on, there's actually a certain amount of like cryptocurrency, right? It gets mined. It gets mined. This is like a controversy. You guys are young. You should know this stuff. It gets mined. How does it get mined? There's a math algorithm. It has to solve a math problem, like a basic math problem. It is all made up, absolutely. But it's a made up math problem that's known to be a certain level of difficulty. So it takes a ton of computing power to actually solve it. And even then there's some randomness associated. So this is Bitcoin, it's mining. But the controversy is this takes a ton of electricity. It takes a ton of power. So it's this made up thing that takes a ton of power. And you guys are like interested in not like, polluting the environment so that you guys don't all die or your kids don't die. But this is like a huge carbon thing. They pollute a lot. You guys don't know this. It's so shocking to me. This is like they have hearings on Capitol Hill and stuff. Like, why are you mining fantasy money?
2 seconds. Those old senators can keep up with all that.
It's okay. Let's just say it's not them. It's like all their staffers and people like telling them about it.
Oh no, those guys don't money. It's the young people like you guys that tell them, hey, this is bad for the environment. Because the computer takes a lot of energy when you've got n factorial, n factorial, n factorial. It gets really big. Computers, you have to have a lot of computers to do that. They have whole like centers.
Maybe we should just look up Bitcoin after.
They're saying that it's good because it increases the amount of power capacity for cities. Like that's how much energy is going into this. It's insane. You guys don't know.
Then somehow it produces money.
It produces fantasy money. Which is okay. I don't know. You like it? I don't have anything against it, except that maybe it pollutes all. I don't really know. I'm undecided. I don't know. You guys control the world now. I'm just telling you about it. Yeah.
It looks like the computer off of.
Yeah. Look at these Bitcoin mining centers. Look it up. It's crazy how much energy it is. Not right now. When you get home, these are all like. It's not a group project. I don't do that.
Like I know it's not correct.
Digging in the computers.
Digging in the ground.
Digging in the old computers.
You guys, it'll be a good conversation starter for your friends.
What are your thoughts on
I mean, even like Matt Damon and these guys, like this is like all popular stuff. The NFTs, all that stuff. You guys don't know about that? This is your stuff. I'm too old.
Yeah, I was just about to say it's possible.
All right. All right. So here's another algorithm. So here's the problem. So what's the problem? There's a word for this. This is an effective thing. This is an effective algorithm. In other words, you can always get an answer. Effective. Can't spell. Effective. But inefficient. You don't want an algorithm. I mean, you want an algorithm that gives you an answer, gives you the best answer. Definitely want that. But you don't want it so that it's going to take you, till you're dead to even not even get halfway there, right? You want like something that you can actually finish. So this works in principle, but in practice is quite difficult. It can be quite difficult if you have a lot of vertices. So let's see if we can find some other algorithms that might help us. This is 6.4. It's called the nearest neighbor algorithm. So the rest of the examples that I'm going to do are going to deal with this, the complete graph. This is K5. It's rich enough that it gives us a lot of examples. So I'm going to a lot of pictures here. So I'm going to explain the nearest neighbor algorithm on this guy here. But let me write it down the step-by-step process, and we'll follow it. Okay, so first step is going to be to choose a starting vertex. And this algorithm will give us a path, which we can then complete the cycle if we want, our circuit, excuse me. Step 2, which is a step we'll repeat over and over again, which is to find the nearest neighbor. So if this is the second step, this won't happen, but we're going to repeat it. So when we repeat it, we have to be careful without forming a circuit. And step 3 is to repeat until we're done. So what is nearest neighbor? The nearest neighbor, if you think of it in terms of cities and mileage, is the closest city. Find the closest city where you're not actually going to form a circuit. So let's give an example. So I'm going to weight this graph here as follows. So I'll give it weights 3. This guy 5, 1, 2. So you can think of these miles, or you can think of them as whatever you light years or okay, I think I've got all of them. Okay, so what you need to do is we need to do step 1. So let's say we choose, for this one, we'll choose our starting vertex at E. At a starting vertex. Now we look at all of the edges out of E, got 4 of them, and we look at their weights. What edge has the smallest weight? Yeah, A, the edge going to A. So we'll choose that edge as our first edge. Now we're at A. And now we have to look at all of the edges out of A, except of course the one we just took, and find the smallest weight. Now we have a couple of options. If you have a couple of smallest weight edges, you can make a choice. So you don't have to, do what you want. So what are the couple of options we have? Someone else? A to C or A to B. So who likes, anyone have a preference? Okay, A to C, sounds good. Now again, we have 2 choices, right? There are B and D. We couldn't go to E even if it were minimal, right? Even if this number here were 1, we can't do that because we'd form a circuit. So we're not allowed to form circuits. So here I'll make a choice. I'll go to B. And now I've got only one choice. And what is that? Where do I go now? B to D. So now I've got my path. So this algorithm does deliver us a Hamilton path for a complete graph. And if you want a Hamilton circuit, once you have a Hamilton path on the complete graph, you just connect the endpoint to the initial. So here we can just connect it. Here I'm gonna make it some. So if I want the circuit, I get that. Now let's calculate the length. What is the length? The weight of this circuit. I have to add all the weights up. So I get 1 plus 3 plus 2 plus 1 plus 4. Gives me 11. All right, great. So let's see what happens if I chose a different starting vertex. So I'm going to undo my path here. So let's choose A as our starting vertex. So if I choose A now as the starting vertex, now I'm going from A to E, right? I go from A to E. That's the smallest. If I look at all these edges, I get 3, 3, 5, and 1. So the nearest neighbor here is E. So let me stop that. Now I look at the nearest neighbor to E. What is that? Someone tell me. I'm sorry? To D. Good. B, right? Now here, what about B? B goes to C. Very good. Let's keep it up. And now I don't even have to look at the weights, because if I connect C to anything except A, I get a smaller circuit. So I don't want to do that. If well, I've got a path. So if I'm going to actually make this a Hamilton circuit, I need to connect the final point to the initial point. So I'll do that. And again, I'll just look at it as, you know, being this extra edge. If I wanted the path, I'll keep only the red. If I want a circuit, I'll keep all the edges with color. So now I look and I'll calculate the weight here. And I get 1 plus 4 plus 1 plus 2 plus 3. Just exactly the exact same. Which is, again, 11. However, I think when I was planning this for the lecture, I was going to make a different choice here. If I made a different choice up here, sorry, this did not illustrate what I wanted it to, which is if I made a different choice up here, I would have gotten a different weight for the path. So maybe I should, well, okay. So in this case, I'm just going to make the comment because I want to move on to something else. So in this case, they're the same, but in general, not. So what I want to do, and we'll see that in a second. So we'll do another example in just a moment. So what I want to say is that this nearest neighbor algorithm does not always give us a path of the smallest distance. So unlike the brute force algorithm, where we know that we can always get an optimal solution, this algorithm, we may not get an optimal solution. So what people do is they'll do what's called the repetitive nearest neighbor. And this just means, so what do you do? Well, you take this nearest neighbor algorithm and you do it for each starting point, and you compare your lengths that you get, and you choose the one that's the smallest. So let's do that here, and I'm going to give a set of weights. We'll do it kind of quickly. But hopefully you'll see a nice. I'm going to give weights, different weights than the ones I just had. $20 here, 21 here. Here. Okay. So we're going to do the repetitive nearest neighbor algorithm with this graph. And as you can see, if we're going to do that, what we need to do is the nearest neighbor algorithm, but we need to do it 5 times. So it's going to be a lot of fun. Yeah. Ton of fun making this problem and even more fun doing it. All right, let's take a look. So let's start. We'll do this kind of quick. Start at A, and you guys have to tell me if I'm making a mistake, all right? And I'm going to do this in a way where I'm not going to highlight everything. I'll draw an arrow. Like easier. So keep track because I don't want to make a mistake. So A goes to C. C will go to D, right? D, if I look at all the options, looks like 1 is the smallest. E, I would like to go to A, but that would make a circuit. So the only choice I have here is to go to B. And then I'm at the end of my possible path, and I can add this to get a circuit. Oops, wrong. I can add this to get a circuit. Okay, correct? Okay. That was A. Let's start at B. So here, 2 is the smallest possible weight coming out of B. So I'll have 2. 1 is the smallest here. 2 is again the smallest here. 1 is going to be the smallest here. And this is the only possible one left. Say something if I make a mistake. I'm going to just keep going. Good. People that are approved, like, put a thumbs up, make me feel like I'm doing all right. Okay, if I start at C, again, 1 has to be the smallest. Here I get to A, and I have only one choice. I can go to B. I'd like to go with 3. 3 is the smallest here, but that would make a circuit, right? That would take me back to C, and so I can't choose that. So the smallest possibility here is this, to go to E along this 20. Then I've got 1 here, so that's that. And then, okay, there's only one choice, and that's to go back to my starting point. Okay. Okay. Awesome. So if I start at D, again, 1 tells me a lot. Now I've got 3 as my option. I got this 1 here. And I can't go back to D because that would form a circuit. So I only can go to B. And then I have to come this way. And finally, I'm going to start at E. And E1 is the smallest edge coming out. I've got 2. I've got 1. And I got 2. And the only possible place I can go from B is back to E. I've got this. How do people feel? Feeling good? I know this class is a little repetitive. That's material with me. All right, guys, so what can you notice about these paths? Did anyone notice anything about these paths? These circuits? Let's see. If I just go over, let me highlight. What do you guys think? Seeing something? These guys, up to a flip in the direction, in some cases, are all the same set of edges, right? Up to changing the direction, it's the same. This guy is different. This one is different. But with the repetitive algorithm, what you want to do is you want to calculate the lengths, the weights. So since I know 4 of them will have the same weight, I can just add for all 4 just that and find that one weight. So let's do that for this last one. This weight would equal, I started at E, so it's going to be 1 plus 2 plus 1 plus 2 plus 20. So that looks like it's 26. The only one that won't have weight 26 is this one where I started at D. And so this one, we can count the weight for that. And I'll get 1 plus 3 plus 1 plus 3 plus 21. And that weight is going to equal what? 29? Right? So what we see is that we do indeed, if we apply this algorithm, we will get different weights in general, okay? And so what we would say for the nearest neighbor algorithm is that the best weight we get from this algorithm is this either this circuit or it's the one with the opposite orientation. So that was fun. I know you guys had a blast. Did we learn anything from it except that there's this algorithm we can apply? What else did we maybe learn from that? So these algorithms are meant to solve a problem, right? They're meant to solve a problem. What is the problem they're solving? We want to find a circuit or a path, right? That has the smallest sort of mileage, right? Smallest weight. So tell me about this graph. Can you look at that and tell me what the smallest one would be? Or a small one? Sorry? That was hilarious. I'm just teasing. Yeah. When you see this picture, what do you see? I mean, aside from some like demonic thing or whatever, like shed that stuff out, please. What? Straight lines. Star. You see the star. Some people will see, people see what they want to see, right? So if we just shade it in, be like a pentagon, right?
Yes, a pentagon.
Okay. So what if we just went along the boundary? What is this total weight you get there? Now I have a question for you guys. What's bigger, 11, 21, or 11, 26? Which one is it, or 29? So I've got these three numbers. What's the smallest number? 11, 29. What do you think? Huh? You gonna go out on a limb?
Yeah.
Say 11?
Yeah.
Okay, how many people agree? Yay, almost unanimous. Some people are too embarrassed to raise their hand. Don't be embarrassed, it's okay. 11 is correct. So what we learned, if we just look at this, and I think if you look at this, okay, I didn't give you enough time, but I really think that if you know, you guys sat down and looked at this picture and I said, forget about this algorithm I just taught you. What's the fastest way to go around this thing where you visit each vertex? You probably would just go around the boundary first and say, okay, yeah, this looks pretty fast. So what we learned is that this algorithm actually will not produce the right answer sometimes, okay? In fact, it will produce an answer that sometimes is over twice as long as the best possible case. So what we learned is that this is an approximate, what's called an approximate algorithm. So it does not always give the right answer. Sometimes it does. Maybe I'll say the best answer. However, so that's a negative. That's a negative for this one. Brute force algorithm didn't have this defect. This one does. On the flip side, the positive side, this algorithm is something we can do very quickly, right? We don't have to go through 20,000 possibilities for this algorithm. So advantage is that this is very efficient. Life is filled with choices, right? So sometimes you have to choose between perfection, the best answer, and speed. All right, guys. One more algorithm. One more algorithm. Cheapest 6.5. Cheapest link. I'll write the steps. First step, find the cheapest, they call it the cheapest link or cheapest edge. That means find an edge that has the smallest weight. Edge with smallest weight. Now, it may be the case that there are several edges with the smallest weight. And then you can just choose one. Step 2. So find the next cheapest edge. However, just like before, well, when we look at repeat, I'll say step 3, repeat. Step 2, without forming a cycle. Circuit, or creating a vertex of degree 3. In other words, when I say creating a vertex of degree 3, I mean on this new graph that you're creating. right, so let me give one example of this. We'll just use the same graph here. Okay, so I look at this. For me, what are the cheapest edges for this graph here? A to C or E to D. So let's choose A to C. Oops, not do that. Choose A to C. Now I look at my graph and I find the next cheapest edge, and the next cheapest edge is A to D. And if I choose it, I haven't formed a circuit, and I haven't created any trivalent or degree 3 vertices. Now I look at my graph and I look at the next cheapest possibilities, and I see the next cheapest edges are CD and AB. And I can choose either. I mean, they both have weight 2. So I can choose either of them, and in fact, I can choose them in sequence. So here I choose CD, and next I'm going to choose AB. And I can do all of that without actually creating any degree 3. See, now each of these vertices still have degree 2 when I think of them in the red graph that I'm adding. Right? They have degree 2 there. I haven't formed any circuit. So now I've actually got a path, and I just have to add this to get a circuit. That's how this algorithm works. Of course, this particular weighting, we never had to make that choice where we didn't choose something because we made a circuit or because we made a degree 3 vertex. So you have to be aware of that if you do it in other cases. Okay, guys, I'll see you on Wednesday.
Thank you.
Yep, thanks.
Sorry to turn in my homework from last week. My tutor was out of